Hello, today I'm going to talk about the stress. Normal stress. Stress is defined as the force per unit area of the material, and the law of stress is sigma equal F over A. The units are Newton over square meter times Pascal, where sigma is the stress and F is the applied force and A is the cross-section area of the object. There are two types of the force in the normal stress. It's the compression force or compression stress and tension. Like this photo here, compression and the tension. And we need also to talk about the strain. The strain is the deformation or displacement of material that results from an applied stress. Normal stress on a body causes change in length or volume. Tangential stress produced change in shape of the body. The ratio of the change produced in the dimension of its original dimension, and that's called strain. That change is caused by forces or couples. The law of the strain is epsilon equal delta L minus L over L. And this law is unitless. There are types of strain: longitudinal strain, volume strain, and shear strain. The types of strain. Strain is, as what you say, it's three types depending upon in change produced in body and the stress applied in the types. Type is longitudinal strain. It's the ratio of the change in length of the body to the original length of the body. Like this here. This photo here, when we have somebody have an applied force here and here, and the cross-section area of the body, and this is the original length from here to here. This is the original length. After the force is applied on this body, will be having a deformation, and this deformation here, it's delta L. Finally, I'm going to talk about the elasticity and plasticity. At any point when we applied a stress, it still behaves as an elastic till another point, where any deformation due to applied stress, it reverses when the force is removed. And this torque is applied here. From the beginning to the point A, any deformation happening here, when we remove the force, it will reverse to its original shape. But in the plastic behavior here from A to B, it will be plastic behavior. That is where the deformation caused by stress remain even after the stress is removed. And we have here the yield point. The yield point where the strain increases faster than the stress, and the deformation is remain. And here we have at point D, where the curve begin to fall. Also we have Hooke's law. Hooke's law, we can apply it in the stage of elasticity, in the elastic, in this stage. And Hooke's law is equal sigma over epsilon. Now I will have some examples to make this more clear, like this example here. Here, find the maximum allowable value of B for the column. The cross-section area and working stress are shown in the figure. Here we have the steel and the timber and the concrete. The steel have 2B, and in the opposite of the way of 2B, the timber have 1B, and finally the concrete have 4B. And every material have a cross-section area and sigma for it. So when we look at this body, we will see in this example show us how the force is perpendicular to the area. So we will take a cut off here and calculate the force from above. So the law is sigma equal B over A. So when we need B, it will be B equal sigma times area. And because the steel have 2B, so we'll put it here, it's gonna be 2B. We have the sigma of steel, 120, and the area is 500, so it will be 30 kilonewton. And for timber, there are 2B, and opposite of the way for it 1B. So the summation of B 1B, and it will equal sigma of times B. The sigma of timber is 120 times the area 2000, and it's equal 24 kilonewton. And the concrete, the summation of forces on concrete, it will 5B, because we have here in the same way, in the same direction, 2B and 4B, and in the opposite of it 1B, so the summation 5B, and it will equal the sigma times the area, and the sigma of concrete is 16, and the area is 8000, and it will equal to 25.6 kilonewton. So, and we will take the smallest value to keep the body safe. So we will use the B for the timber, because it's the smallest value. So the working B is 24 kilonewton. I will have another example. The timber members has a cross-section area of 1750, and its modulus of elasticity is 12 gigapascal. Compute the change in the total elongation of the members after the loads shown are applied. So here in this question, we need to calculate the elongation in the timber. The law of elongation is BL over EA. At every point here, there are a different B, so I will have a cut off here and take the B of point D. It's 20, and the L is because it's kilonewton, we need to make it Newton, and the L is a 3, the E is 12, and the cross-section area is 1750. So the first elongation will be 2.857 millimeter. The second elongation at point C, it's in the opposite way, so we will have the summation here, and it will be 15, and 1000 to make it Newton, and the long is a 3, 12 and the same area 1750. So it will be minus 2.142 millimeter. The third elongation at point B, we will have the summation of the three forces that applied here, and it will be 25. And the long here is 1.5. 12 on the same area 1750. So it will equal to 1787 millimeter. In this question, he wants the total elongation. So we have to take the summation of the three elongations to have the total elongation. So S total will equal first and the second and the third, and it will equal to 2.857 minus 2.142 plus 1.782, and the total elongation will be 2.5 millimeter.